Okay, we're good. So we can go for it.
Okay.
So part 2, did you cut out your little squares?
No, I just went to that little website and got them, so I have the name.
Okay. So randomly select 5 of the 30 salaries and then compute the mean.
Okay.
So I think we both, I don't know, do we each randomly select different ones?
Yeah, I did that. Mine were 6, 10, 22, 27, and 30, so I have my means. So
6, I'll get mine so you're on the same page. What'd you say, 6, 10?
22, 27, and 30 are the ones I selected. So
27.
do we have to select the same ones, or are we supposed to have different ones?
Well, I think it would help if we selected the same ones because
Okay.
then we'll calculate the same numbers.
Okay, perfect. Yeah, 6, 10, 22, 27, and 30.
27. Okay, so 6, 10, 22, 27,
And 30.
and 30. Okay.
Mhm.
Let me calculate my mean real quick. Okay, what did you get for the mean?
484220.
Okay, that's what I got too. Okay. Okay, so B is this graph illustrates the sampling distribution of the sample mean. There are 142,506 possibility combinations of 30 salaries drawn 5 at a time. This graph represents the distribution of all possible samples. Make a mark on the horizontal axis to indicate the value of your sample mean for part A. So ours is 48.
So what are the little lines? 20, 40, 60? Oh, they're 25, 50, 75.
Yeah.
So we got
48. Okay. Does our mean appear usual or unusual?
it's usual, isn't it? It's like a little bit to the right, but
Yeah, it's a little bit left skewed, but it's pretty usual. Okay. Compare your mean from equation 7a to the means obtained by at least 3 other individuals. Oh, maybe we were supposed to pick different ones.
okay.
I'll pick some different ones.
Okay.
Calculate their means real quick.
I can do it some different ones too.
Yeah,
For
if you want to do
sure.
one different one, yeah.
Okay.
Okay, the mean that I got was like dead center on the top of the bell curve.
Okay. And then I got one that was 45,480. So closer to the center.
Yeah, closer to the center. It's pretty close.
Yeah.
Most of them are pretty close. Okay. The Graduate Management Admissions Test, the GMAT, is used for admissions criteria in many Masters of Business Administration programs. The scores on the GMAT are normally distributed with a mean of 529 and a standard deviation of 113. Consider the random sampling of n equals 10 students taking the GMAT. What is the shape of distribution of sample means for all such samples? Well, it should be normal.
Because it's normal.
Yeah.
Because
Yeah. It's a normal bell
because
curve.
they're normally distributed, so our sample ones should be normal.
Yeah, should be normal. Okay, it says, how do you know the distribution of the sample mean has this shape? Well, because they're normally distributed. Otherwise, it would be normal if it had a higher n score.
How do you know this? Yeah, because if it's a normal distributed mean,
Yeah.
right?
Or if it has n higher than 30.
Right.
Otherwise, it'll be skewed towards whatever side the data is already skewed to.
Right.
Okay, so what is the mean of the sampling distribution of the sample scores for all such samples? That's 529.
Right. 529. And then the standard deviation would be the 529 divided by the sample.
No, it would be the standard deviation is 113 divided by the square root of the sample.
Oh yeah, where's that little thing? It's the standard deviation divided by the square root of 10.
Yeah, so 113 divided by the square root of 10. So it would be 35.734.
35.73. Yep, that's what I got.
Okay. Yeah, that was the only activity that I think we had to do. Let me see if they have the answers for these ones in the back of the.
You know what, I have it. Let me see. Normally distributed, parent population is normally distributed, so those are right.
Yeah.
The mean
529.
of the sample is equal is 529 in that one.
35.734. So cool. Yeah, we can start our group quiz now. I looked at the group quiz last night.
Oh, good.
So.
And how does it look?
I think it's pretty good. I think we can figure it out.
Okay, true. True.
Okay, so when taking samples of n, when n is 5, what is the shape of distributions of a histogram when the parent population is right skewed? Should be. What do you think? I think it's right skewed.
I think it's right skewed because 5 isn't a very high number.
Yeah, it has to be. It said in the back of the book, n has to be greater than or equal to 30 for it to be high enough to make it normal.
If it's right skewed in the first place, right? Okay.
Yeah. Okay, so skewed right. For when taking sample of n equals 100, what is the shape when the parent population is right skewed? That would be normal.
It should be normal.
Yeah. Okay, 5. When taking samples of n equals 100, what is the shape of the distribution of means histogram when the parent population is normally distributed?
Normal.
Should be normal, yeah. Okay. When would the distribution of means be normally distributed? Choose all the correct responses. One is data are drawn from a population that is normally distributed and the sample size is small.
So that one's right.
Yeah. The next one is data are drawn from a population that is normally distributed and the sample size is large. So that one's true.
Okay.
Data is drawn from a population that is right skewed and the sample size is small. That would be false. Yeah. And then data are drawn from a population that is right skewed, but the sample size is large. That'd be true. Yeah. So those 3 would be true. Okay, which of the following gives the best explanation of the central limit theorem? That one's the one where if sample size is large, the shape of the distribution of the sample size x will be approximately normal.
Okay.
That's what I got.
If the sample size is large, the sample mean will be close to the population mean.
No, that's
if the sample size is
numbers.
large, the shape of the sampling distribution of the sample will be approximately normal. So it's the bottom one.
Yeah.
So because that one's the
population.
shape, right?
Yeah.
And the other one's the accuracy.
Yeah. How close it is to the standard deviation is law of large numbers.
Okay.
Let's see now. Okay, let x be a random variable with a population mean of 10 and a population standard deviation of 6. Suppose a sample size n is 36 is drawn from this population. What is the mean of the distribution of means? 10.
10. Okay.
What is the standard deviation?
So that would be, ours is 0.6 divided by the square root of 36.
I think it's just 6.
Oh, I said 0.6, but it's just 6.
Yeah. Divided by 36. So it'll be 6 divided by 6, so it should be 1.
Right.
So when it says 3 decimal places, do you put 0, 0, 0?
1.00?
Yeah, I think you put 1.000.
Okay. Well, and if not, it shouldn't bug it. We shouldn't be in trouble for that.
Yeah.
So I'm going to make sure I did that right again. So 6 is the standard deviation. I divided by the square root of 36, which is 6.
Yeah.
Divided by 6 is 1. Okay, good.
Okay. Regardless of the distribution of the population, if the sample size is large, where n is greater than 30, what would be the shape of the distribution of the sample mean?
Normal.
Normal. Yeah. What theorem would justify a response to question 10? That would be the central limit theorem.
Okay, but regardless of the distribution of the sample size, wouldn't that be the law of large numbers?
No, because
we're talking about what would be the shape.
Yeah, of the mean. And the law of large numbers, yeah.
Yeah.
The law of large numbers only talks about that the mean and the standard deviation will be really close together.
Right, and the central limit has to do with the shape. So that, I think that's the biggest thing right there.
I think so too. So, okay, let's just maybe go through them again because there wasn't that many. So 3, when n is 5,
the
and
shape
it's right
is
skewed.
Right skewed.
Right skewed. Okay.
Right.
4, when taking n is 10, the shape is right skewed. What will appear to be normal? Should be normal. Yep,
normal.
That should be right. When taking sample n and the parent population is normal, should be normal.
Right.
When distributions of mean be distributed normally. Data is normally distributed. Both normally distributed will always make normal distributions.
Right.
And then
when it's with a large size.
Yeah, that should be right. Okay. Which of the following gives best explanation of the central limit theorem? If sample size is large, then the sample distribution of the sample mean will be approximately normal. Right. I think that's right. I'll go check on the book definition real quick just to
because it's not the second one and it's not the first one, and it doesn't really have to do with the mean. It has to do with the shape.
Yeah.
The shape is really what we're looking at, the distribution shape.
Yeah. Okay. Yeah, that's right. I think that's right.
Yeah.
The
X being random.
So
the mean is always the same 10. The population.
Yeah, that's always 10.
Yep. And that's 6 divided by the square root of 36 is 1.
Yeah.
And if we put 0.000, it's still 1, so it's not a big deal. So.
Yeah. If it is, then we need to text our teacher.
Yeah.
Regardless of the distribution, if n is greater than 30, it will always be normal.
Right.
And then that's the central limit theorem. That should be all right.
What theorem would justify? Okay, now I'm still, okay. Regardless of the distribution of the population, if the sample size is large, what would be the shape of the distribution? Is the only reason that that's central limit theory is because they're asking the shape, not the other.
Well, also because the central limit describes what's happening to the shape of the distribution of the sample means, like you said,
Right.
when the sample size is specifically large.
Okay.
So I think that's why, and it even says that right there, because n is greater than 30, which is a
Okay.
large sample size.
Okay. I'm good with that.
Yeah. So I think I think we'll submit it.
Okay.
Got 100.
Nice.
Cool.
Nice job.
Yeah, good job. Mackenzie missed 100 this time.
Okay. Hey, thanks,
All good.
Colton.
Yep. We'll see you tomorrow or Wednesday. Sorry.
All right. See ya.